Multiple allele. Let's talk about the very concept of multiple allele, which we always visualize as an exception to the Mendelian concept. Now, how it is an exception to the Mendelian concept? For this, first of all, let's learn what exactly is a multiple allele. We know very well that in the eyes of Mendel, the gene can be represented only in two alternative forms. For instance, take an example of height. So it can be either capital T or a small t. But now we know very well that gene can exist in more than two alternative forms, right? And when gene exists in more than two alternative forms, we call them it's a multiple allele. Okay? But the important thing is that all allelic forms is going to occupy the same locus, right? But the important thing is that all allelic forms is going to occupy the same locus. So what exactly is a locus? Okay. So if you see, if I draw, or let it be say it is a homologous chromosome, right? So let it be say it's a capital T and here let it be a small t. So this T or this position of allele is actually called as a locus. So suppose capital T or gene for T has a three allele, let it be T, small t and T1. So according to multiple allele concept, either of these three at a time can be occupied at these two fixed locus. So it can be T, small t, or it can be small t or T1, or it can be capital T or T1 and so on. So allele is also always going to occupy the same locus. Multiple allele follows all law of Mendel. So they follow the law of segregation, they follow the law of dominance, right? But still we call them as an exception. Why? Because it is an exception to Mendelian hypothesis. Mendel hypothesized that the gene is going to exist only in two alternative forms, which is not the case. So that's why it is only an exception to the hypothesis. Okay. Now let's take an example of multiple allele, that is ABO blood group. Now you see this ABO blood group is controlled by a single gene, and that is going to be represented by three alleles, I, IA and IB, right? Now there is a fixed relationship among these genes. Okay. So what exactly is the relationship? The relationship is that IA and IB both are co-dominant. Okay. And individually they are dominant to a small I. So this is representing what we call co-dominance, and this is representing what we call dominance, right? So this gene is located on the long arm of 9th chromosome, and we know very well gene encodes glycosyltransferase, that is an enzyme which modifies the carbohydrate content of the RBC antigen, eventually forming three different forms, right? So let's see that how these three alleles are together going to form different blood group. So you can see there, this is the blood group A that can have a two possible genotype, IA and IA small I. So this is going to be the antigen that is on RBC is a A. Similarly, IB is going to be represented in two alternative form, but for AB, they can be represented in only one form, IA and IB, because they don't have any antibody, right? And blood group O is going to be represented by homozygous small I, and they don't have any antigen. So they consist of only antibody. Okay. So this is how the blood group is like that. So we can say that number of genotypic and phenotypic class in ABO blood group is 4 and 6 respectively. So what are the phenotype? This is 1, 2, 3, 4, that is the phenotype. And what are the genotype? So this is a 1, 2, 3, 4, 5, 6 genotype, right? We can also calculate the number of genotypic class for any gene having an allele by a formula, that is n into n plus 1 by 2, where n is the number of alleles. Okay. For instance, if you take this particular example, here we see that the number of alleles is 3. So if I keep this value in a formula, then what we are going to get? That is we're going to get 6. Okay, and that is why this is the 6th genotypic class what we see over here. So that is the formula that we have to use whenever such questions are asked, right? Now let's see some of the questions. What is the number of phenotypic and genotypic class for a gene having 4 alleles? Now solution is very easy. First of all, we have to calculate as per the formula. So we know very well number of genotypic class is equal to n into n plus 1 divided by 2. So altogether we get n. But mind it, phenotypic class cannot be determined, because for phenotypic class we need to understand the relation among the alleles. In the question, the relation among the alleles are not known. So that's why we cannot say about the phenotypic class, right? Let's take one more question. What is the number of heterozygotes in a population for a gene having 4 alleles? Now, in order to solve this question, first of all, we have to calculate that what is the total number, what is the total possible number of genotypes. Again, by the formula, we can calculate the total number of genotypic class as 10. And we know very well, if we take a 10, that number of homozygotes is possible only 4, because there are 4 alleles. Let's take an example. Suppose there is a A, B, C, D, 4 alleles, right? So what are the possible homozygotes? A, B, B, C, D, D. These are the only 4 homozygotes are possible, right? So these 4 homozygotes are possible. So naturally, rest of the things are going to be heterozygotes. So if I subtract 4 with a 10, then we are going to get this particular answer, right? So this is how this is actually calculated. So that's all as far as the verification of multiple allele is concerned. Okay, thank you.